Okay, everyone. Well, why don't we go ahead and get started here? Hi, I'm Jacob Andreas. I'm new faculty in the ECS department and CSAIL, working sort of broadly on natural language processing and machine learning. And what I wanted to talk about today is some recent work that we've been doing in the group on basically building natural language processing systems that can learn from more unusual kinds of supervision, and in particular, that can learn without having to collect a bunch of natural training data, and we'll go into the details of what that looks like in a minute. Before we start, let's see if I can make this work. Yeah, before we start, I just want to say that most of what I'm going to be talking about today is led by my student Alana Marzov, with Sam Madden, Franz Kashik, and Mike Caffarella, more kind of over on the system side of things. So let's dive into this. One of the sort of big things that we want to do in natural language processing generally, and the sort of kinds of things that we want to build, are natural language interfaces to software systems, right? So it might be the case that if I have like a database of information about restaurants, I want to give people the ability to ask questions, complicated questions, right? Like what neighborhood has the most inexpensive Thai restaurants, and to automatically be able to map that sort of unstructured natural language input into some kind of structured executable representation of meaning that I can then hand off to a computer system that can go out and actually compute the answer to the question. For example, by running a little computer program or running a database query or something of that kind. So, you know, generally we want to build to allow people to interact with software systems using the language that they speak. And as I sort of suggested a moment ago, what we're going to be looking at today is tools for building these kinds of natural language interfaces using only the kind of training data that we're showing in red on the bottom left of the slide here. Sentences that are in fact not generated by human beings at all, but that are instead generated by some kind of synthetic data production procedure. So how can we learn from this kind of low quality fake data in a way that still allows us to build robust and generalizable systems that can actually handle real user utterances? So when we talk about natural language interfaces, first off, like what are the kinds of problems that we are trying to solve? And one of them, as we just suggested, is the problem of question answering, right? So if I have some structured knowledge source and a human comes to me asking what neighborhood has the most inexpensive Thai restaurants, I want to be able to answer that question on the basis of whatever information is contained in this knowledge source. Similarly, we might want to produce answers to questions in a format other than natural language, right? So I might want to map from a question like, how are sales looking this week, not to some sort of single fixed answer, but to some kind of, you know, time series plot or bar chart or even more complicated visualization that contains the answer to this question, where again, you can basically think of this as a problem of mapping from a natural language string to some sort of little computer program that knows how to generate a plot of the particular kind that we're interested in. And you know, there are more sort of complicated versions of this as well. If we think about instruction following problems, for example, in the context of like household robotics, I want to be able to instruct some sort of automated agent, go right into the living room and stop by the rug, and have it actually execute that sequence of actions in some sort of like real household environment, like we're looking at in the video on the left. So in this case, you should think of the sort of mapping that we're trying to construct as not from natural language strings to computer programs, but instead as a mapping from natural language strings to like low-level robot actions or low-level motor controls in the environment. But structurally, the problem is basically the same. I have my input coming in the form of natural language, and I want to map it into some sort of, you know, lower level instructions that a computer system knows how to understand. So these are the kinds of things that we want to build. Oh, yeah, and actually I'll say one more application where this is particularly interesting is machine teaching. So if I think about having this household robot deployed out in the world and I want to give it new skills, The way we mostly train machine learning systems right now is you collect a bunch of like demonstrated examples of the particular behavior that you're trying to do. So if I want my robot to be able to bake a cake, I have to collect a million examples of, sort of people baking cakes, and then I can train it to do that. This is not how people learn to bake cakes. People learn to bake cakes by reading recipes. So we might similarly want to be able to provide natural language specifications of procedures for implementing new behaviors or for achieving new goals or whatever. Here's an example from a video game, but you can imagine sort of real world examples of this as well. So these are the kinds of problems that we're thinking about in the context of building natural language interfaces. How is it that you actually go about building such an interface nowadays? And pretty much the only tool that we have is to do something like this, to go out and collect a big data set where on one hand you have your natural language inputs, and on the other hand you have structured representations. You have these kinds of sequences of low-level computer understandable actions, and you're trying to learn a mapping between them. We have, in some cases, more sophisticated techniques for example, learning question answering systems just from question answer pairs without these computer programs in the middle, but they're a little bit harder to scale. And in general, when we're building real world systems, we're building them using training data that looks like what we have on the slide right now, where you have a bunch of pairs, where one component of the pair is a natural language sentence or a natural language query, and the other component of the pair is this structured machine readable representation of meaning. And as a practical matter, if you want to construct a data set like this, basically the only way to do it is to find someone who sort of knows these programming languages well enough, or to build special demonstration and data collection tools that actually allow you to pair these things with natural language strings. And you need to come up with some way of eliciting sort of all of the interesting questions that you think your real world users are going to ask before you've actually had a chance to deploy the system for real world users. So the high level point here is just that we really rely on these kinds of data collection procedures before we can even start thinking about machine learning problems for building NL interfaces, and data collection is really hard to get right. Now, I would contrast this with a sort of something else that's going on in the NLP field right now. And so if you're sort of paying attention to NLP, you may have noticed sort of a lot of buzz in the last like 12 or 24 months around these big pre-training schemes, things with names like Elmo and BERT and GPT, that are basically all about building like large probabilistic models of sentences and just learning to like take an input sentence and fill in some pieces that were missing, or take a prefix of a sentence and generate whatever comes next in the sentence. And these kinds of large-scale pre-training procedures have led in many cases to like really significant improvements in the state of the art for a bunch of natural language processing tasks, things like machine translation and doing question answering about documents, and various other more kind of linguistic analysis flavored tasks. And it's natural to ask whether some of these benefits might actually sort of also change the way we build these natural language interfaces, where we're trying to do something in the world and not just reason about text. And one important point here is that the training data for these kinds of tasks looks very, very different from the training data that we were looking at a couple of slides back. So right here, the kind of data that you need to train something like BERT or something like any of these other like big pre-training schemes is just text, right? I can go out onto the internet and I can scrape a data set of 1 million or 1 billion websites and get all of the text from them and just learn to basically predict the words that are coming next or predict the words that are coming in the middle. And it's maybe not surprising that like if you have a bunch of product reviews in this data set, you'll learn relationships between meaningful quantities of these product reviews, right? That like even relatively complicated things like the fact that something becoming a favorite is good good, but that also like being sad that it's gone away is a positive feature for the product. And so we can learn like good and relatively complicated relationships among sentences and among other things like star ratings that get expressed in text. What we don't get, or what, you know, it seems to be the case right now that we don't get at all from this kind of large scale text data, is any understanding of what these words actually mean in terms of how they ground out in any kind of real world behavior, right? So I can know that seeds becoming a favorite means I have a high star rating, and means I'm going to say things like I'm sad that they've gone away from the store, or I can know that, you know, a bad review is likely to include the word tasteless. But this model has no idea what tasteless means, or what taste is, or how taste grounds out in the world. And I would contrast that, again, with the kinds of problems that we face when we're building these sorts of natural language interfaces, which are really all about not relationships between sentences or relationships between text and text, but really about, fundamentally about relationships between natural language and the world that it describes. So if you're gonna follow an instruction like go right into the living room and stop by the rug, at some point somebody has to show you what a rug looks like or what a living room looks like, and no amount of text data on its own is going to help you do that. So at some point, you know, we're committed to using more training data than just is available for these kinds of large pre-training schemes, and again, training data of a very different kind, and of a kind that's much harder to collect because it isn't just like naturally occurring and harvestable in quite the same way. So what does this mean practically for you know, software engineer or developer or whatever who's out there in the real world trying to construct a new natural language interface from scratch? And a typical sort of development workflow for somebody working in one of these situations looks a little bit like the following. Start out by building some kind of fake data set, just so that we have some data that we can sort of debug our machine learning models on, and make sure all of the other pieces of the plumbing are working, and so on and so forth. And so a pretty typical way of doing this is to just write down a little grammar that says, you know, for example, when I see a sentence that's like placeholder with the largest placeholder, then I'm going to map that onto some sort of arithmetic expression on the programming language side. When I see the natural language word neighborhood, I'm going to map that onto some special variable named neighborhood on the programming languages side. When I see the string number of blank, I'm going to map that onto a string that looks like this. And then if I take all of these rules and combine them, you know, build a grammar out of them, sample from the grammar, then I produce sentences that look like neighborhood with largest number of restaurants with Thai cuisine, and a plausible looking program that goes along with that. Now, you know, the important thing to notice here is that the sentence that we've generated at the bottom, neighborhood with largest number of restaurants with Thai cuisine, is almost certainly not a restaurant, is not a sentence that any user of this system is ever going to actually produce, right? It sounds like it was spoken by a robot because in effect it was spoken by a robot, right? We sort of have some synthetic data generation procedure that's producing these things. So they're really not all that useful as training data for any kind of system that we want to put out in the world, but they look enough like natural language that they're useful for doing whatever it is that we have to do next, which is like starting to tune the machine learning piece of this process and the sort of fundamental like software engineering piece of this process, right? So I need some model that can take any kind of string and map it to these programs on the other side. And then of course I need implementations of these programs themselves. And so in the course of building out some kind of new natural language interface, the kind of data that we produced in step one is good enough for these things, even if it's not good enough to produce a final model. And only once I've done these things, once I have a model that I'm reasonably sure is going to be good enough to solve my task, and I have implementations of all of these things that I can use for actually like building interactive tools or interactive simulators or whatever, do I actually go out into the real world and collect real natural language utterances from people. And so, you know, people, if you prompt them in the right way, will ask you questions not like neighborhood with largest number of restaurants with Thai cuisine, but rather, neighborhood with the most Thai restaurants, right? Which is a much more natural way of asking that question, and various other things like find a kid-friendly Italian restaurant. One really important point to make here is that you can try to, write your synthetic grammar on the left side of the screen in such a way that it produces much more natural sounding questions like the ones that we're showing on the right side of the screen. This is really, really hard. And there were like decades of research in NLP, basically before the advent of statistical approaches, where people tried to do this and tried to build really high quality rule-based language generation and language understanding systems. And all I'll say here is that like those tools exist. This is a point we'll come back to in a minute, but they require a huge amount of work to use. And in some ways, it's actually even harder to try to do this all in a rule-based way than it is to do this really hard data collection thing that we're doing on the right side of the screen. So, yeah, so just to say this again, this data collection procedure is really hard to do properly. It's hard to like prompt annotators to ask interesting questions. It's hard to get interesting variation if you're using Mechanical Turk. There's a bunch of work you have to do just to like make sure that people are not cheating and sort of typing in meaningful or meaningless sentences, but in ways that are hard to detect. So step 3 is really more even than the machine learning, the bottleneck to getting one of these kinds of systems out in the real world. And so what we would really like to be able to do, and what we're going to be looking at today, is tools that let us basically bypass this third step, that let us start with this synthetic robot language generated by a rule-based procedure on the left-hand side of the screen, do all of our work and all of our model building just with that data, and still be able to answer questions like the ones that are in box 3, even though we've never seen any of those questions at training time. And the sort of relevant analogy here is to what's called sim-to-real transfer, which is something that's pretty widely studied at this point in robotics and in computer vision, which sort of have the same problem. Slightly different constraints, but basically where collecting real-world data is really hard, in that case because it's slow and because you can work much faster in simulation than you can in real environments. There's been a huge body of work built up both in the vision literature and in the robotics literature on exactly this problem. I'm taking sort of synthetic 3D rendered scenes that live entirely inside your computer and building from those things robot policies that you can actually execute on robots that are working out in the real world. And so what we are essentially trying to do today is to come up with some analog of this sim-to-real transfer technique that works for natural language processing. And at a technical level, it's actually going to be quite different from what people are doing, but it's a problem that exists in other domains as well. So just to say that another way, this is the analog of what we're trying to do. We have our synthetic sentences on the left, we have our natural sentences on the right. Okay, so how are we going to go about doing this? There are two sort of, and I guess to lead into this, what Alana has developed here is really a wonderfully simple and sort of elegant way of solving this problem that we're going to go through too, that's based on 2 key insights. The first of these insights is that if your space of fake sentences is rich enough, and by that I mean rich enough in the sense of capturing all of the kind of variation in meanings that people might try to express, even if it doesn't capture all of the variation in ways that they might express it. So if for any sort of kind of question that somebody might try to ask, I have in my fake data generation procedure a robotic version of that question, then this sim-to-real transfer problem for natural language processing basically reduces to paraphrase, right? That when somebody comes to me with a new sentence that I've never seen before, like neighborhood with largest number of restaurants with Thai cuisine, first of all, I can build, I can train my model just on the synthetic data using the procedure that we were looking at before. But importantly, when somebody comes to me with a new sort of natural sentence, like neighborhood with the most Thai restaurants, all I have to do is find the synthetic sentence that sort of means the same thing as this natural sentence that came in. And to make this point a little bit clearer, for any given kind of question that I might be trying to ask, in general, there are many, many different ways of asking that question, right? What's the best neighborhood for Thai food? Can you tell me which neighborhood has more Thai places? And so on and so forth. And these are all asking you to run the same database query and to produce the same kind of result. And a lot of what's kind of hard about natural language processing, and a lot of what you're having to do with these big data sets for machine learning is to annotate all of the variations in ways of asking the same question. So if we could just find some sort of mapping from real sentences to synthetic sentences, then we would basically be done with the problem, because as we saw before, it's really easy to sort of generate as many of these synthetic sentences you want and build an arbitrarily large data set out of those. So this is insight one. And insight two is, once we've cast this as a paraphrase detection problem, this is now something where we really can bring to bear all of these fancy pre-training techniques and all of these large naturally occurring data sets that a couple of slides back we said were not actually all that informative about these kinds of interface building problems, right? Because now we're asking questions not about the relationship between sentences in the world. We're just asking about relationships between sentences and sentences. It happens to be the case that some of those sentences are synthetic and some of those sentences are real. But if these models are really big enough and robust enough, then they don't care about that distinction. And so to sort of say this concretely, what happens here is that I can take a sentence like neighborhood with the most Thai restaurants and get some sort of vector representation of that sentence using one of these big pre-trained models. Similarly, I can take a sentence like neighborhood with the largest number of restaurants with Thai cuisine, which, we said was, I guess, a more robotic version of the question. And if I hand that off to one of these big sentence embedding models, I'll again get a representation of that question, such that those two representations from the model standpoint are much closer to each other than they are to representations of sentences that correspond to totally unrelated questions. So basically, we're breaking the problem into two parts. We're going to use fake data to encode the relationship between sentences in the world, and then real data or real representations of sentences learned at the large scale to figure out basically what stylistic variation looks like, and not all of this information about how things ground out in the real world. Okay. And that's basically it. And with these two ideas in mind, you can now develop a very simple procedure that basically gets you most of the way to doing well with this problem. This approach has two pieces. The first piece here is that we're going to take our natural language sentences and we're going to project the space of natural language sentences on the space of synthetic sentences that are generated by this model, using this notion of sentence similarity that we've learned from big unsupervised corpora. And then having done that, we'll feed this fake sentence that we got from our projection step, and we'll feed it to some model that's only been trained on fake data, that's only ever seen fake data, but that gets really high accuracy on that kind of data. So this at a high level is how things work. And to state this a little bit more formally, we're basically building some sort of projection operator from fake sentences or from real sentences to fake sentences that looks like this. Given a real sentence X, I want to find the fake sentence X tilde that has the property that it's as close, that it is closer rather to the real sentence than any other fake sentence that I might choose, where for the time being, our definition of closeness is defined by one of these big pre-trained representation learning schemes like BERT. So this is the sort of model in a nutshell, and everything that I'm going to talk about now is just what you have to do to make a procedure like this actually work in practice. There are a number of things about this basic model formulation that are actually pretty challenging to work with. The most important of these is the fact that there are lots and lots and lots of fake sentences, right? So even if I'm not trying to capture stylistic variation in language at all, the number of distinct meanings that I can express in the context of a question answering problem or an instruction following problem is still enormous, right? For like very, very simple domains, you get on the order of thousands of these things. And in general, there might be sort of infinitely many or at least like millions or billions of these things. And so we definitely don't want to have to do a brute force search to compute this argument, to find the closest fake sentence every time somebody comes to us with a new query, because this is just going to take unacceptably long. So we're going to get around this basically with some clever data structures. So there's been a bunch of work on sort of fast nearest neighbor search and fast inner product search, and we're basically just going to be able to exploit that in this system. So we're going to build up some kind of data structure and some kind of hash function in particular that has the property that two sentences with the same hash are likely to be located close to each other in vector space, and then we can bucket these things by hashes. And again, there's like a sort of whole large literature on these fast inner product searches, and we can just drop in any of these in order to make this search procedure quickly, or to make the search procedure fast. Now, this is good in the sense that when somebody comes to us with a new query, we can now do this search very efficiently because we only have to look at its neighbors in hash space, and there are going to be, in general, many fewer of those than there are fake sentences in general. But we still have to construct this nearest neighbors data structure up front once. That's still an operation that's going to take linear time in the number of fake sentences, of meanings that I might try to express, and that is still going to be unacceptably large for general versions of the search problem and for general natural language interfaces. Oh yeah, sorry, this is just another way of saying we can put things in buckets such that things in the same bucket are close to each other. Right, so to make this point again, just to construct this nearest neighbors data structure, there are still too many of these fake sentences for some problems for us to even be willing to construct this whole thing up front once. So here what we're going to do is actually break this problem down into pieces as we're generating individual sentences. So one of the important things to notice here is that the space of fake sentences that we're dealing with has special structure, because we know it was generated not by some human user just like enumerating fake sentences, but instead by writing a grammar with little rules like number of in natural language maps to the length function on the programming side, and so on and so forth. And so we can actually sort of start to do this search procedure that we were doing on the previous step in the process of constructing one of these fake sentences to begin with. To make this concrete, this is what this looks like. In my grammar, the rules of my grammar generally are of the form, start with some sort of symbol and expand that symbol into a fragment of natural language on one side and a fragment of a computer program on the other side. So if I start with the root symbol in some grammar that somebody has written here, and I try to expand it, I might get something that looks like this in the context of an instruction follow, right? So I can produce sentences that are open, followed by some sort of noun phrase. I can produce sentences like go to, followed by some sort of noun phrase. And I can produce sentences like put a noun phrase next to a noun phrase. And maybe these are the only sort of meanings that are expressible in the context of my instruction following problem. Notice again that each of these sort of sentence templates is in general going to expand to a very, very large number of sentences, more than we can possibly enumerate. But right now, at the sort of top level of this grammar, we only have these three possibilities to consider. And so what we're going to do is we're going to immediately start to prune our search space by just saying which of these three templates is closest to the sentence that I'm trying to interpret to begin with. And what's important now is that I have some notion of sentence similarity that's well-defined, not just over sort of complete natural language sentences, but also over these kind of weird fragmentary sentences like we're looking at on this slide that say open blank, go to blank. What's cool is that we actually get this for free with a lot of these standard pre-training schemes, which are already designed for reasons that we're not really going to go into today, to produce good high-level representations of sentences with big chunks taken out of them. So this notion of sentence similarity that we were using a couple of slides back continues to be a useful notion of sentence similarity, even in the case where what we're looking at is not a whole fully instantiated sentence, but instead a sentence with a big bite taken out of it. So I'm going to compare each of these top-level rules in my grammar to the natural language input query that we got based on this notion of sentence similarity. And maybe I'll notice that this one, this third rule, is in fact the one that's most similar. And so now I'm just going to search under expansions of this rule. Now, there are a bunch of ways of filling in these symbols, right? as before. I can replace this first hole with, you know, the noun phrase a blue box or a red sphere or a couch or whatever else. And each of these corresponds to a slightly more fleshed out instantiation of this template that still has some holes in it for the second spot. I can take each of these ways of expanding the first symbol and again pick the one that looks most similar to the query that I was starting out with and continue to search through here. So what we're doing now is that we're basically building up one of these, oh, and I'll say if you have large numbers of ways of expanding these rules, which is going to happen, for example, like at this phase where we're filling in a blue box, if your vocabulary size is really large. What's nice is that you can actually sort of build up this nearest neighbors data structure like we were looking at a couple of slides back, just for expansions of individual rules. And so what we're essentially doing is we're taking this, this search that we had to go through for the previous argument steps, and we're doing it incrementally. We're basically constructing one of these nearest neighbors data structures on the fly, such that the set of candidates that we're considering are only candidates that look like they're likely to be useful based on the top level. So we never have to instantiate the full structure, and we save time basically always and not just once up front by doing that. Yes, and so this is basically the trick. There's a bunch of other stuff that you can do to improve the quality of the scoring function itself by exploiting structure in this grammar that we're not really going to talk about today. But this is basically the approach in a nutshell. What's nice about it is that what it looks like from the perspective of somebody who's trying to build out one of these new natural language interfaces is I have this like black box paraphrase machine. You feed it a sort of set of grammar rules as input, or even just a set of sentences, synthetic sentences paired with their interpretations as input. And now I have a sort of black box device that whenever somebody gives me a real sentence, I can produce the best fake paraphrase of that sentence and hand that off to whatever my model is. So I construct this sort of procedure once, and then really all you have to do to build out one of these new systems is to write your grammar. And that will give you both the set of candidate fake sentences and all of the training data that you need for the actual instruction following or question answering model. So how well does this actually work on sort of real world tasks? We're going to look at experimental results now on a couple of different benchmarks, the first of which is actually a data set of questions about restaurants. So if you just take your synthetic training data and you train sort of a vanilla neural sequence-to-sequence model just on the synthetic data, and you don't use any other resources at all, you can only answer about 25% of the questions. If you then take that and you throw all of the best like sequence modeling, pre-training, whatever machinery we have at the problem, you use these pre-trained representations for your input sentences, but otherwise treat this as just like a normal sequence-to-sequence learning problem, then you can answer about 36% of the questions. And if you instead do this projection step like we've been looking at before, you get all the way up to 43% exact match on these questions. So one thing I'll say is that the number of answers you get right is actually a little bit higher than this because sometimes there's ambiguity in the structure of the program itself. But the main takeaway here is really just that sort of posing this as a projection problem buys you a lot over treating it as a normal sequence-to-sequence modeling problem, even when those two models have access to the same set of features and the same set of representations. Maybe even more remarkably, if you actually take the data set, the fake data set that we train this model on, and you go out and you get people to generate natural language paraphrases of each of those real or of the fake sentences, and you train on those natural language paraphrases. So this is a model that, unlike our model, actually knows what natural language looks like and knows what sentences outside this training distribution look like. You don't get any better. So even with a little bit of real training data, you cannot beat, in this particular data set, this projection-based approach that uses only fake data at training time. To look at this in another domain, here's a sort of synthetic instruction following domain that's really popular in the reinforcement learning world. You get, you know, in the sort of standard version of this data set, instructions like open a blue door, to which the agent will execute some extended series of actions like we're looking at right now. and the version of this problem that people mostly work on is one where you just see these synthetic data set or these synthetic questions. It's really about generalization and reinforcement learning. We were interested in seeing how well you could get any of these instruction following models to generalize to natural questions as well. So we actually went out and got a bunch of humans to generate natural instructions for these kinds of agents, and again applied the same technique that we were looking at before. And the story here is more or less the same, that, for sort of reasonably sized data sets, if you just, I have the first two bars backwards here. The projection approach gets 63%, I think, discounted reward, which is not a meaningful number in an absolute sense, but gets 63 there. The seek-to-seek model that we were looking at before gets 54%. And once again, if you try to fine-tune this model on a little bit of the real natural language data that we collected, you get better, but you don't actually get up to the performance of this projection-based approach. So the high-level intuition here seems to be that it's pretty, or it's comparatively easy to build like a really robust model when you just give it synthetic data. When you start trying to train on mixtures of synthetic data and real data, or you fine tune on a little bit of real data from a model that's been pre-trained on synthetic data, it's easy to overfit or easy to overstress the capacity of the model or whatever. And so you would really rather disentangle the kind of paraphrase part of the problem from the language grounding part of the problem. And that's what this projection approach does. And it's why it's able to do get a score of 63 here, get a score of 43 here, and so on. So that's it for experimental results. And I guess in the little bit of time that we have left, I just wanted to talk about some next steps that we're thinking about for these problems. The first, of course, is that you can almost certainly do better than just using like off-the-shelf word embeddings or sentence embeddings for this distance function that you're using for the projection step. There is lots of like supervised paraphrase data out on the internet. There are machine translation data sets. There are annotations on there's a big data set in Quora of whether pairs of questions mean the same thing or not. And you can imagine using all of this data to give you a better similarity function. And one of the nice things about this framework is, again, that learning that similarity function is totally separated from the question of learning how these sentences actually ground out in the world. So we can continue to use other kinds of like richer but text-only data just to learn this piece of the model. Another direction that we're kind of excited to explore here is actually to go back and revisit this old school NLP literature on building grammars. So one sort of important feature of all the experiments that we were looking at today is that we weren't the ones who were doing the grammar engineering ourselves. We were taking pre-existing sort of fake language data sets that were out there already, intended for uses other than just training on them directly as the only source of training data. And so we imagine that you could do much better if you actually sort of basically spend as much time optimizing these grammars as people typically spend optimizing machine learning models to do well at these kinds of tasks. And again, there is a large literature on rule-based ways of doing that and engineering tools for helping you do that. People sort of mostly stopped using these rule-based approaches because they top out at somewhere well below 100% accuracy on any of these tasks. There's just always going to be a long tail of things that's hard to model. And the hope would be that this kind of approach is actually something that you can use to take the kind of 70 or 80% solution that you get from grammar engineering tools and just turn them into a 100% solution. So some sort of unification of the older grammar engineering literature with modern representation learning approaches. And finally, the sort of main learning problem we've been looking at today is one in which you never get to see any natural language data ever while you're constructing this model, and it only comes to you at test time. This is sort of representative of what it looks like when you're trying to build out a new system from scratch the first time, but it's not necessarily representative of the problem that people who are running these systems have once they've been out there in the wild for a long time and you see people interacting with them and so on and so forth. So, in some ways, the largest piece of this is to figure out the semi-supervised learning story and to figure out what the right thing to do is when you have both a lot of synthetic data and some amount of natural language data already paired with your downstream annotations from which you could imagine learning directly. And that's it. So just to sort of wrap up here, We presented an approach for building sort of language understanding systems generally, or natural language interfaces in particular, using only synthetic training data generated by some like low coverage grammar. And the key idea here was to use pre-trained word representations to induce a similarity function on sentences, and then to map input utterances to synthetic counterparts that we know how to interpret. This is like in the Q&A archive right now, but if you're interested in reading the paper, it is online on our group's website. And I will stop here and take questions. So thank you.
Thank you so much, Jacob. We do have a few questions. The first question, when mapping real sentences to synthetic sentences, how might you incorporate references or context from previous utterances? And the example given was, quote, what are the top 5 Thai restaurants near me, end quote, followed by, quote, what about Italian restaurants, end quote.
Yeah, that's a great question. So there are a couple of different ways in which you could sort of get beyond the sentence level here. One of them, of course, is to just like incorporate these kinds of discourse level phenomena into your synthetic data generation procedure, right? So I can write my grammar in such a way that when I'm referring to an object a second time, I generate some kind of pronoun or some kind of more complex referring expression to pick it out. The other is just to note that, and I guess I don't actually know sort of empirically what the behavior is. I would guess that if my natural language inputs are, include all of these kind of referential phenomena, and my synthetic inputs don't. So my synthetic inputs in place of everywhere that I might insert a referring expression, just like literally specify the object that I'm trying to refer to again. I bet that if you produce contextual representations of those sentences, they're still pretty close to each other. But that would actually be interesting to look at as a way of like seeing, even kind of independent of the problems that we're looking at today, the extent to which these systems can deal with or sort of abstract over modes of reference in the induced similarity.
Another question we received was, will the system suffer from synthetic data? Because models learn synthetic sentences much easily by fitting some shortcut rules. One serious example is that the ABI dataset reaches 100% accuracy pretty soon.
Yeah, so to make sure I understand, is the concern that you're going to overfit on these synthetic sentences, or and like not be able to generalize over synthetic sentences, or something about the similarity function itself? Because like I guess the issue with the baby data set is just that it doesn't like the set of phenomena being expressed is small. Maybe this is hard to do with the bottleneck for question answering, but I guess at a high level, I'm not, the important constraint on these fake languages is that you get good semantic coverage, even if you don't get good coverage of lexical variation.
I just asked for follow-up, so we'll see. Another question in the meantime was whether have you thought about using cycle consistency principles to learn in an unsupervised way mappings between synthetic and real data?
Yeah, that's a great question, right? So you could certainly imagine treating like this problem as an unsupervised machine translation problem where I have my natural sentences on one side, I have my fake sentences on the other side. You could probably like fine tune with an objective that looked like that. The important thing here is that unlike the normal supervised machine translation setting where you really get a lot out of cycle consistency constraints, like these things are already in the same language, and we already start with a representation space in which things that mean the same thing are pretty close to each other. So in some ways we're starting from a better initialization, but you could certainly imagine doing fine-tuning using something like a cycle consistency constraint.
And Jacob, is this research public to anyone outside, or how can people find more about information about this?
So the code, certainly the a software implementation for this projection operation that we have on this slide and our annotations for the baby AI data set are going to be online. I think we haven't posted them yet, but they will be soon.
Okay, great. Thank you. I believe that's all of the questions I received. Um, so we thank everyone for your time. Thank you, Jacob, for hosting today. We also have a number of Alliances events upcoming. So if you're still on the line, please sign up. Um, but yeah, thank you so much.
Great. Thanks, everyone.